Okay, thank you for the introduction, and I'm happy to be here. So we'll straight jump into it. So the first part will be the part of the master thesis, but it will be heavily focused on the jets. And then we move to the short GRBs and Kilonovae. So just a quick outline. So the blue part, AGN, Blazars, and the second red is the AGN and the blue is the gamma ray burst. So in the AGN, I will talk about the basic introduction, the problem that I want to solve, and then some numerical simulation, and from there, radiative transfer and synthetic imaging. And in the gamma ray part, in the short GRBs and Kilonovae part, we'll discuss what is the main landscape of the problem, and then what are the complications and what we are trying to do, and how what we are doing would be useful. So at least the landscape of the active galactic nuclei is such. And is there a pointer? Okay, thank you.
Right. Okay.
So the general understanding is that we have a very supermassive black hole at the center, and around that we have an accretion disk, and the relativistic jet is sort of a bipolar emergence from that. And just to bring this into real observation scenario, this is the M87, the famous EHD shadow. And just as a comparison, the solar system is really small compared to it. And this is the ALMA image of the jet. So we have our system, the black hole, the accretion disk, and then the jet. So from simulation, these things look like this. So the main landscape of AGN, we need a black hole, we need an accretion going on, and then we can expect to have a jet. But then we go further. So just I focus first here and then come back here. So if we look at, okay, we take real images, and then we see that the jet morphology is much different if we keep on taking different, studying different objects. So in this case, the M87 jet, you see that the jet morphology is very narrow. And if you compare this one with the 4C45, let's call it that, and then the jet morphology is very blobby and it expands much more compared to this one. And over here, there is a good description about it. So this is the M87 jet. So on the bottom, you have the distance from the core. So if this is the black hole, so this would be how far away you are measuring your distance, and this would be the jet radius. So as you move away from the black hole, your jet radius and your distance from the core is all of the data points are just falling on the same line. But after you exit the strong field regime of the black hole, so this could be the vertical line here, Bondi radius. So this is generally effective field 10 to the 5 Schwarzschild radius. After that, your jet morphology changes. So for the main purpose of this talk, I'm going to completely ignore the strong field part, but the important point, the two important point here, so the jet morphology can be very constrained. And then again, when you look at them, so they appear very different. So that means intrinsically something different is happening. And the problem of interest, at least for this talk, is the effect of magnetization and ambient pressure on the jet morphology. So magnetization would be within the jet, the ambient pressure would be outside. So this is the main problem of interest. And then a very brief part of the simulations. So first we ignore this and also ignore this, just this part. So we solve special relativistic magnetohydrodynamic equations in cylindrical coordinates. And our model is a spine sheet model. So you have the jet spine in the very center, and around that you have a sheath. And you can practically remove a lot of complications with that. And then you can put a numerical grid on that. And this is just some, these are some details of the numerical simulation. And over there are some of the physical parameters that we put inside by hand. And it's basically the relativistic regime with the adiabatic index of 13.9. So you have relativistic electrons, as we expect. And then we construct three models. So ABC, and what's the difference? So this column, this would be the magnetization, and then the ambient. So let's focus on the ambient. So ambient is the, let's say, the medium or the space into which we launch the jet. So by that, I mean, if you look at kappa 0.4, so this would be the ambient into which jet is launched, and this is, it's much more overpressured compared to the jet. And if you take the extreme value of kappa 1, so then in this case, the jet is moving very freely. So these represent in a semi-log plot our ambient conditions. And at the very end of the first part, we will visit this plot again, and then we'll put a different profile into it. And the initial conditions of the jet. So this would be the jet radius, and till one jet radii, this would be the nozzle of the jet into which we launch our jet. And outside that, we don't touch anything. So we only change values at the very onset of the injection. After that, we do not touch anything and then let it propagate freely. So you have velocity. So this is important that there is a sound speed. So this generally remains stable. And this would be the L-fin speed. So this will depend upon the level of magnetization. It can be below sound speed if you have, let's say, very low magnetization, and can go really high. And then the jet velocity as such. And then the pressure looks like this. So inside the jet, or at least in the injection region, we have high pressure, and outside the jet, the pressure is low, but the density is different. So this would be overpressure jet in a highly dense environment, but then some of the magnetic field contribution. So in the phi and the z direction. And just to come back to the sigma, so the two parameters that will be mostly important, sigma and kappa. So in the jet, very close to the spine, your sigma is generally higher. So, and then as you move outward, this falls off. And once you do all of this, so the initial output of the simulation looks like this. And this I've chosen where you have very low magnetization and the ambient is very weak. So you just see in, let's say, exaggerated detail that how different sections of the jet are. So this would be the density, this would be the propagation direction, and this would be the radial direction. So your jet is going in this direction and it is expanding along the radial direction, and the pressure and the Lorentz vector. So what you do is you launch your jet in the one RJ, so jet radius, and then from here you let it propagate. So what you see that over here, so you have started your jet, it is propagating, and then it is interacting with the ambient, and then the reactions are coming back to your jet spine. So this part would be expanding very freely because most of the deposition of energies and velocities in this part, and then you start developing shock layers, recollimation shock, and then they interact with the jet spine, and then this moves forward. So just a basic, let's say, the structure of the jet that we have recovered. And then now we are still in the RMHD domain, but what we do is we try to change our variables and then see if in the simulation itself we see some changes. So this would be, we only change magnetization, keeping the ambient values fixed. And over here we change the pressure profile is changed. So what I mean by here, so you have magnetization increasing. From here to here, your magnetization is increasing, but the ambient is the same. So what you see that when you have a very weakly magnetized jet, the structure, the internal structure, and also the outer edges are completely different. So in this, all of your bumps are not, let's say, if you look at this point and these 2 points, so they are not following the jet morphology closely. And if you look here and over here and over here, so the jet velocities are much more fast because of high magnetization. So the structure changes, but you can quantify also all of this, but just to give you a brief idea that by changing the magnetization, you start seeing a very strong spine contribution. And then what you do is you change your kappa value, which is the ambient outside, and then your sigma remains same, which is the magnetization. So when you launch your jet into a really heavily dense environment, so what you do is your jet is coming back more frequently, and then these oscillations are very high. And when you allow your jet to expand into, let's say, much less dense environment, your jet can expand more in the radial direction, and then the whole morphology is different. So just to initial results from the simulation. And then what we want to do is we want to bring all the RMHD equations into radiative transfers. Okay, sorry. So till now, what we have is the RMHD. So, and now what we want to do is we want to really go towards the frequency flux space, and then later on build synthetic imaging. So for the radiative transfer, what we have, our jets, we image them in a grid sort of this sort of setup. So you have a jet, and then this is also 3D grid, but just for the visualization, you see a 2D part. And then in each cell, what we do is we compute the RMHD, so the radiative transfer. So basically you want to recover the intensity. So ds then becomes every cell, so jet length. So basically we compute emission and absorption in each cell, and then all of the flux correction are accounted, luminosity distance. And then we start going from code units to real physical units. So these we can change, but of course we try to be realistic. And then further, I go with the first basic idea of the, so this would be the spectrum in frequency flux. And then what you see is in this part, so this part, if you solve the radiative transfer equation, so this would be when you are optically thick. So in this part, you start with, let's say, low intensity, and then later on you have a turnover frequency. So this would be a case where we have viewing angle of 3 degrees, sigma 1 and kappa 4.75. So this is generally the case which I will mostly show, as you see here. And then when you go into optically thin part, then the things become different. So by solving this, this is really depending upon the magnetization. So what is the real game here? So you start in the optically thick part. So you don't actually see anything inside because your optical depth is such. So you increase the frequency and then you start penetrating deeper into the jet. So this would be the same case with the traffic light, what you see in the fog and all this. So this is just to establish that the behavior over here from optically thick to optically thin, constrained by the magnetic fields. And then in the radio images, what you see from starting from really optically thick to really optically thin, you see the spine of the jet. So the quick implication here is that if you really want to penetrate deeper into the jets and see their internal structure, you need to go to much higher frequencies. So, and if I change the parameters and I pump up the density, then you can actually, you really need to go to 230 gigahertz or even higher in realistic scenarios. So, and then what we come back to is we change the ambient pressure, as I was showing you earlier, the 3 panel plots where you have, by changing the ambient pressure, the jet was expanding more, and in one case was really narrow. And we bring all this into the radiative transfer, and then this part. So these are for different ambient condition with the fixed magnetization and the viewing angle. So we generally keep everything at 3 degrees because we say, okay, we want to analyze blazars. And then what you see is, okay, there is nothing, not in the sense like completely, absolutely not there, but still, interestingly, no big differences are there. So you start with very same behavior in the optically thick, and then you move to optically thin. But the effect that you can have, or you can see, okay, this jet is in much dense environment compared to this jet. Only you will get this behavior, or you will observe this if you do the imaging. And our initial assumption in the analysis from the RMHD part is reproduced here. And then I go forward with the magnetization. So over here, as we recall in the optically thick part, so there was inverse dependence on the magnetization. And over here, there was a direct dependence. So the more magnetized jet will have higher emission in the optically thin part because there will be a strong contribution from the spine. But if you have a jet which is very low in magnetization, the effect will be, the final emission will be very less. But from here, so there is nothing that you can see, okay, which is the jet which is highly magnetized and weakly magnetized. But this is, let's say, encoded in the radio images. And the part that, okay, frequency is the same, but then you see in this, you already see a very strong spine. So I move forward from here. So, and then now this plot, first I talk about this, better I talk about this. So what we see is that in the realistic scenario, you cannot have a single profile in the ambient pressure. So in the realistic scenario, as you move outside, away from the center of a galaxy, what you have is a drop in the density and the pressure. And this is generally taken as a broken power law profile. And over here, what you have is the initial cases which I showed you with the kappa values from 0.4 to 1. And on top of that, what we do is we take a realistic case which should resemble something like a broken power law, what we observe, and then along the propagation direction at roughly 100 RJ in the Z direction, we put a second profile. So this is the way to sort of mimic a more realistic jet. And then we go forward, and what, at least now I do not show the single lit spectrum, I just focus on the morphology. So this would be a jet at a 3-degree viewing angle, 15 gigahertz and 86 gigahertz. And now what is happening in this is, so the ambient has a broken power law. So roughly till 0 to 100 RJ in the Z direction, you leave one profile, and then after that you allow it to expand more freely. So our previous results that, okay, if you increase the magnetization, your spine becomes more apparent. And also if you have really low magnetization, you will never actually have a spine. And when you go at 86 gigahertz, then of course you see more inside the jet. So if you compare this and this image, so you will see that the boundaries are, let's say, very dim here. And in these parts, you actually go inside the jet. But now what is the outcome of putting a realistic profile that from our simulations and the radiative transfer on top of that, basically the whole ray tracing scheme, what we can at least recover is this expanding blobby morphology. And later on, we can analyze more on this, but for the scope of this talk, I stop some of the analysis there. And now what I show is I take the model jet, some of our fiducial models where you have put a broken power law, and then we convolve them. What we want to see is we want to predict in a way that how realistic telescopes would see. So you put the same models and then allow the convolving. And then at 15 gigahertz, what we were seeing that, okay, you would not see the spine of the jet. You would not really go deep into the inner sections of the jet. But when you go at 86 gigahertz, so the jet would change and it would look like this. So this is generally this package which is being used to reconstruct radio images also for the EHT. And over here, I bring the first part, the summary of the first part. So what we wanted to understand was the behavior of pressure and magnetization on the jet morphology. And basically, we call them jet oscillations, combining the reconfinement and recollimation shocks. And then what we see when you have a really strong magnetization, so you inject more energy into the jet, and this is really dominating the spine part of the jet. And these signatures are more clear in the images rather than the spectral signatures. So now we sort of change the, how much time? 5 minutes? Okay, so I will not drink water. So I move forward and I go to electromagnetic counterparts. And this is the work that I'm currently doing. So the focus is on the short GRBs. So what are short GRBs? They're very different than the long ones. Why? Because the long ones have, they emit for much longer duration. And the short ones, if you plot all of the observation and see them, they are falling below 2 seconds, and also the hardness ratio is much different. And I do not focus on long. So why short ones are important? Because they are much more complex and they are required. So the landscape of the short GRB, which is the compact merger, is that you have neutron star or a neutron star black hole, and over time when they eventually come close, they can merge, and within this merger you have a scheme which looks like this, that after the merger you have the ejected masses, and then you have a launching of jet, and within that you have a cocoon. And this process is heavily dominated by R process elements. So this is the rapid neutron capture part, where you need a really neutron rich environments. And this is also shown here. So only then you can produce really heavy elements, which we see. And the further scope of this whole process is, so you have to start from the binary properties from the out, and then link the outflow properties, that how much mass is ejected, what are the velocities, and then you actually go to the light curves. But our approach is going from this part in this direction. And there are details are like, once you have a relativistic jet, you are sensitive to viewing angles, and the details of the merger and the ejecta are, again, a more complex scenario comes into the picture, that what are the progenitors if you have a neutron star, or if you have a black hole neutron star. So this case is relatively easy, because if you have a black hole, you are eventually always going to form a black hole. And then depending upon how close or where your ISCO lies and what are the details of the initial merger, you may not have a lot in emission. And then if you have neutron star, so you may form a black hole, which is an easier thing, and you may have a short-lived hypermassive neutron star. And these properties, there are a lot of details in the equation of state, in the mass ratios, in the asymmetries, if they are like angular momentum is conserved during the merger or not. If the angular momentum is not conserved, then you would have much more emission, mass ejection. So what you start to do is, okay, you say, okay, after the merger, I have a neutron star. In one case, I have a black hole. So your density distribution is very different. And when you have R process elements, so what you want to do is you want to understand the electron fraction. So this is the, how many electrons do you have compared to the baryons. So in this case, where you have a neutron star as a remnant, your electron fraction is much more different compared to the one where you have a black hole. And all of this is imprinted on the light curves. So I speed up a little bit. And what do we see in the light curve? So what is the kilonova and the afterglow? So we saw that in the merger, what we eventually see is a jet, and then things around the jet, which are in the merger plane. So if you look at the contribution from the jet, it is basically a forward shock synchrotron. And then what you see at late time, you start seeing some re-brightening. So what is this? So what we say afterglow is the contribution from the jet, and the kilonova is the emission from radioactive decay of nuclei. And this is coming in thermal. So you see that this is arriving at late time. And then you also see, okay, in the spectral evolution, do we see something similar? Oh, yes, we see. So you have the afterglow. Okay, we can model it, but then there are some data points which are not synchrotron. So these are fitted by thermal contribution. This is the sign or actual kilonova. And a big challenge is that what if the kilonova is always below your afterglow? So you will never see it. So coming to what we are planning to do. So our envisioned outline of the work is that we'll utilize the sample of the past short GRBs. So since this is the entire element of transient astronomy, so these events, so earlier I showed you the 2-second window, and then the data points you can still recover till few days. If you go into radio, you're still safe, but you have to capture all the data very quickly. So that's why the samples are generally low. So we start with a sample of all the short GRBs with known redshift. And redshift is important because we want to constrain all of the fluxes. And then what you want to do is explore the kilonova models with kilonova parameter space with the models. And then we will use UV optical near infrared and the X-ray bands, and we'll explore all the database. And then from there, we will put in the models and we will constrain which model fits the kilonova the best. And then still these are things which are model dependent, equation of state, asymmetries, velocities. So one model cannot really describe. And then in the process of sample building, we start with a total currently known 73 samples. And then we put a constraint that everything has to be below 0.5 redshift. So we actually have some signal that it's not embedded below the afterglow. And then, so this is just an initial way of showing, okay, we have a lot of data points, but when we start putting our constraints, then we have really low data set, but still the quality of the data is nice. So just to show, this would be the last slide, and then I finish with a summary. So this is a kilonova GRB 160821b. And in these two models, okay, we have some data points. So we cannot right now say, okay, so afterglow plus kilonova, but we know the kilonova is generally peaking at late time and in the near infrared band. So what you do is, okay, you take your model in which you say, I may have some geometry from the post-merger, and into that I put some density profile, into that I put some electron fraction, and then we say, okay, what would be the R process contribution? There are many more things, but I will stop. So then you say, okay, you take a model where you fix your ejected mass, and you take a model where you fix the geometry, and in this you, after fixing the ejected mass, you change the geometry parameters, and you try to see if you can recover the data point from the kilonova, and you do the same. And in the future, we are going to do this process in much more detailed way in many more models. And with that, we hope to say, okay, if your models are, let's say, predicting much higher values, let's say your model is saying your light curve is here, but your data point is much below that. So you can start saying that this much mass was not ejected in this event and this. So you start building your conclusions and then going towards the parameter space and bring the compact mergers possible from binary neutron stars or black hole neutron star. And merger is the process of producing short GRB. If you have a collapsar, you produce a long GRB. And then the observed properties strongly depend upon the merger. So equation of state, your asymmetries, your spin, there are many parts which still are under development. And then disentangling kilonova and afterglow are difficult. So, but we are still, that's the only way this has to be done. And we are going to explore all the past short GRBs and hopefully some nice events in the future, and then identify the signatures of kilonova, and then eventually going back in the domain of the binary properties, outflow, and then the light curves, equation of state dependence. And I stop here, and sorry if I took some.
Okay, so are there any questions?